In this last segment, we'll consider how we find distances out to cosmological expanses. So there are many methods, and basically it's called the distance ladder because one method builds on the previous. So there's multiple methods, not all shown here, and we won't go through them all. But it's like climbing a ladder. You have to hit the first rung before you go to the second, the third, fourth, and fifth. And so this is the basic approach that's taken. You measure the apparent brightness of an object. You use a technique to discover the intrinsic brightness, or how bright it really is. And then the distance modulus equation can discover the distance. Apparent, absolute magnitudes, and there's the distance. And then establish standard candles to progressively go deeper into the cosmos, as the ladder technique is indicating. So in that way, we're able to actually discover, to a fair degree of certainty, cosmological distances. I'm just going to highlight a couple of these methods. The very foundation, the very most basic and unambiguous type of measurements comes from radar. We can literally bounce a signal off a planet, say Venus, and we have a time for the round trip signal, which is moving at the speed of light, c. So you bounce signals off the planet, you get precise distance from the time it takes. Distance is rate times time. But because we have a round trip, it's only half of that. So distance is rate, that's speed of light, that's the rate times the time divided by 2, because it's only half the round trip distance. From this, the Earth to Sun distance has been very precisely and accurately measured to 1.496 times 10 to the 11 meters, which is 150 billion meters. That's an astronomical unit, and it is very precise, very unambiguous. And it is the foundation from which, now that we have a platform, Earth moving around the sun, we know exactly how far away the Earth is, we can now make accurate determinations using parallax. Parallax is something we already discussed. Of course, it's limited, but it's the next measurement technique, which is direct. That's why it's so important. Stars farther away have smaller parallax angles, and soon the angles get too small to measure with our technology. Ground-based measurements limited to about a 50th of an arc second, or 100 light years. Now this is changing, so it's a moving target. I don't know how accurate the 50th of an arc second is, but it's in that ballpark. That gets us out to about 100 light years into the galaxy. The Hipparchus satellite took about 120,000 parallax measurements of stars at 10 times this resolution, not being limited by the atmosphere. So it got to about 1,000 light years into the galaxy, but the galaxy radius is 50,000 light years. So we are just a small fraction of actually measuring the entire galaxy. We're just kind of getting our toes wet even with this. However, there is a mission called the Gaia mission. I think it's supposed to launch in 2013. That's a moving target also. But it's slated to have a resolution of 0.00001 arc seconds. And with that kind of resolution, to be able to detect parallax angles, it will be able to determine directly distances and velocities of stars throughout the entire Milky Way galaxy, which will be an awesome project because it will enable us to get a correct and accurate three-dimensional view of the galaxy we live in. So I'm really looking forward to that. Remember the Cepheid variables? We alluded to the fact that they are useful for discovering distances. Well, now you're Cepheid experts, so this should make a lot of sense. Well, at the lower end of the period luminosity relation, we have the RR Lyrae. They're also lower luminosity, about 50 times brighter than the sun. Hubble telescope can observe these out to about 1 megaparsec, or about 3 million light years away. And of course, the Cepheids are much brighter than that. And especially the type 1, the high metallicity ones, which are the ones we find in the disk. The type 2, the low metallicity, they have already been used to discover the distances to the globular clusters and pinpointing our location in the galaxy. So the type 1 high metallicity Cepheid variables, we now have a variable star that's bright enough to actually be seen in other galaxies. So we've escaped the galaxy, and here is an example of a Cepheid brightening, and it's really hard to see exactly what's going on there quantitatively, visually, but CCDs can actually count photons, so we can get a very precise and accurate determination of exactly how bright, how much luminosity is being produced by the Cepheid variable in the disk of this galaxy. They're about 10,000 times brighter than the sun, which they need to be. And even using Hubble can get out to just about the Virgo cluster, about 18 megaparsecs. So we're really starting to extend our reach with a particular object where we know its intrinsic brightness. We can measure its apparent brightness and get the distance. The next rung on the distance ladder is perhaps the most important step to discover very distant objects. So let's see how this works. We have two images here of NGC 1309. A Type 1a supernova was seen in 2002, observed by the Lick Observatory. There it is. Pretty incredible event. Well, since then, we have had observations from Hubble that have been able to pick up Cepheid variables. Remember, the Cepheids are 10,000 times the luminosity of the sun. Hubble can pick them up 100 million light years away. So it's picking them up in this galaxy. It's the very limit of Hubble's ability to see a Cepheid. So there it is. And now knowing the actual distance to the galaxy, we can go back and knowing what the original supernova brightness was, we can plug it into the distance modulus equation and find out that the intrinsic luminosity of a Type 1a supernova is minus 19.5. Well, that's wonderful to know because they all go off at 1.2 solar masses. They're all the same intrinsic brightness. This is a standard candle. Every time you see a Type 1a supernova go off, you know it has a luminosity corresponding to a intrinsic magnitude of minus 19.5. So we have a new tool to measure distant galaxies with a bright Type 1a supernova, luminosity 10 billion solar masses, and this enables us to literally span the cosmos with our distance measuring tool. The Thule-Fisher relation is a method of determining distance that's not really on the rung of the ladder. It's not based on the others. It's independent. It's based on rotation rates of the galaxy. And as you recall, neutral hydrogen in a galaxy, which is abundant, has a 21 centimeter spin flip transition photon, the 21 centimeter photon flipping from high energy to low energy spin states. And of course, it produces a spectrum, the 21 centimeter spectrum. The measurement of Doppler shifts of that spectrum is an indication of the velocity of the hydrogen gas orbiting around the galaxy. So based on the broadening of the spectrum, we have an understanding of the rates at which the gas is moving around the galaxy. More massive galaxies, the dust and gas orbit quicker. And then based on the fact that it's got more mass, it's also going to be more intrinsically luminous. So in this way, we can get the rotation rate giving us an indication of how bright the galaxy is. So we have luminosity, intrinsic luminosity, and rotation rate. That line is called the Thule-Fisher relation. So if we can discover the rotation rate, we come up here and plot it, and we get the luminosity. Isn't that a wonderful little tool? Well, in fact, it is. And so you can then, once you know the intrinsic velocity, you compare it with the intrinsic luminosity, you compare it with the apparent brightness to get the distance. So this too enables us to observe distances cosmologically out to distant galaxies. And it's wonderful in the sense that it's an alternate way, not based on the other methods. Remember the Hubble relation? The recession velocity versus distance? Well, this is Hubble relation 2.0. with higher tech measurements and much deeper measurements, observations of galaxies very far away, and actually measurement of supernova in these distant galaxies, we have the Hubble relation to much greater accuracy, because it's very important to understand the Hubble constant, because the Hubble constant gives us information about distances to distant objects, as we saw. So this is modern data from Cepheids and supernova. The limit of Hubble's original data. His original data was confined to just the local galaxies. So it's just this small little region right here in comparison to the scale that we're seeing here. And the problem is that galaxies that are close together tend to be gravitationally interacting. So some of their motion is not really manifesting the general expansion of the universe because they're gravitationally bound with each other, like the Milky Way and Andromeda galaxy. Very close galaxies, that would actually produce a blue shift because Andromeda is moving toward us. In any case, as we look at all this data, we arrive at 72 kilometers per second per megaparsec being a very good modern value for the Hubble constant. At cosmological distances, the relative motion of galaxies in a cluster, which causes blue shifts and red shifts, if it's around us, if it's far enough away, the general expansion of the universe is going to be so much greater than those peculiar velocities of moving toward or away from each other as a result of their gravitational interaction, that those small velocities will essentially be washed out. It's kind of like if you're observing a ship that's in port and there's a dog walking along on the ship, you'll notice the motion of the dog with respect to other things on the ship. And that's significant. If the ship is moving away at, it may not be a good example, but if it's moving away at, say, a couple hundred miles an hour, then the motion of the dog walking along or a person walking along, that little 2 mile per hour motion compared to the 100 or 200 mile per hour motion is relatively insignificant. So it works that way with distant galaxies as well. So an overview of the different techniques. We've looked at some of these, some of the common methods. We talked about radar ranging. It's not even shown here, but next is parallax. We discussed that. We skipped over this spectroscopic parallax, and our Lyrae and Cepheid variables. Cepheids are visible for great distances. The Thule-Fisher method and the type 1a supernova. In addition to that, we have the Hubble law, and just bolstered that a little bit. Once the Hubble constant is known, it's a snap to get the distances. Modern value of the Hubble constant, about 72 kilometers per second per megaparsec. The recession velocity is the Hubble constant, the slope of the line times the distance. Don't worry if that just confused you a little bit. But you get a spectrum of the galaxy. You obtain the velocity from the redshift. That's the recession velocity, VR. The distance is recession velocity divided by the Hubble constant. There you see that formula again. It's very useful because the spectrum of the galaxy or the distant luminous object is easy to obtain, and you get the recession velocity from the shifting of those absorption lines. And the Hubble constant is, unfortunately, not real certain. So the limitation on the usefulness of this is that Hubble constant. But nevertheless, this is very easy to apply, and it applies to cosmological distances. So this will conclude this particular lesson.